Hello, everyone. Today we're going to discuss our machine learning project. Our project name is Predicting Product Return Reasons Using Machine Learning. What is machine learning and why is it important for companies? Well, machine learning is a subfield of artificial intelligence. It allows the system to automatically learn and improve from experience without being explicitly programmed. Our introduction for this project is we'll have to address the problem, which is this project investigate the underlying causes of product returns in a logistic and supply chain environment. These returns contribute to financial losses and customer dissatisfaction. Why is this problem important? Product returns cause disruptions in inventory. This leads to higher operational costs and often signal underlying quality or logistic issues that need to be addressed. How do I approach this? We'll use a real world data set of product returns. We'll apply a classification algorithm and we will use models like NIME and IBM SBS modeler. Related world, we have used previous research that uses decision tree, naive Bayes, and random forest for similar tasks. Our work will expand on this by using a wider range of models on domain-specific dataset across the two platforms we've specified. So our data source is provided by the doctor or our instructor, and it contains real-world product return records, including features like price, size, product status, etc. Our data amount is 300 to 500 records, 8 to 10 features per record, and we have mixed variable types. First off, we'll start with the figure 1 dataset. We have independent variables or features like size, price, product status, production place, etc. Then we have dependent variables, which are the target, the reason for return, which will be our output. This was converted to label target column called target class, formatted as class 1 and class 2. The performance data, the model performance was evaluated using metrics such as accuracy and confusion metrics. So each model was tested using a holdout set after a train test split. In NIME via partitioning, and SBS is via data prep and type. So a presentation analysis in NIME, the data preparation involved a missing value handling, data type conversion, string manipulation, and one hot encoding. An SBS modeler, auto data prep was used for cleaning, followed by the type node to set rows and measurement levels. We'll also use models visualized like tree diagrams, confusion matrices, etc. So for data cleaning, missing numerical values were handled using imputation or default settings on auto data prep. String to normal conversions and number to string formatting were applied to allow proper class labeling. Irrelevant or redundant columns, such as unique identifiers, were removed from the training process to avoid noise. We had feature selection also. Only features with meaningful patterns related to return behavior were included, and the unimportant ones were removed. For future importance, in NIME's SPS modeler outputs, product status and production place consistently ranked as the most important predictor. Now for the algorithm and definition. We had figure 3 SPS model stream, then we have figure 3.2 NIME workflow. For decision tree in the algorithm, it's used to supervise learning model. Its function is to split the dataset using features that minimize impurity. The algorithm steps will be starting at the root node with entire dataset, choosing the best features to split based on impurity reduction, then repeat the splits recursively until stopping criteria are met. We'll assign the class label to leaf nodes. For random forest, it's a model that builds multiple decision trees and average their protection for accuracy. The function is to reduce overfitting and variance by combining multiple weak learners. Our algorithm steps will be drawing random bootstrap samples from the dataset, then train a decision tree on each sample using random feature subsets, aggregate the protection using majority fault classification, then the output the final class protection. For naive bias, it's a probabilistic classifier based on bias theorem. The objective function is to maximize the posterior probability of each class given the feature. Our algorithm steps will be calculating the prior probabilities for each class, estimating the likelihoods of features given a class, compute posterior probabilities for new instances, predict class with highest posterior. Then for shade or chi-squared automatic interaction detector, it's a tree-based algorithm that uses chi-square test to find the best splits. The function is to find most significant feature interactions based on statistical tests. Algorithm says we'll start with a full data set, then merging the categories with similar response distribution, then perform chi-square test to split nodes, and then stop when b-value exceeds the threshold or max depth is reached. Then we have the tree AS, which is the automatic selection. It's a SBS smart tree algorithm. It uses multiple tree types, tests multiple tree types. The function is to automatically maximize accuracy while minimizing complexity. The algorithm steps will be input clean dataset, internally run several tree algorithm, select best model based on internal scoring and output the selected tree structure. Choosing a model to train, all the models were trained using supervised learning. In NIME, the partitioning node was used to split the dataset into 70% training and 30% test data, and SPS data was processed using auto data prep and split implicitly during training. Each model was trained independently using the same feature set and compared based on accuracy and confusion metrics. And now for part 3.5, my friend Maimuna will continue.
Can you see my screen?
Yes.
Okay. All right. Now I'll take over starting from section 3.5, model evaluation metrics. So after training all our machine learning models, we needed a way to evaluate how well they performed. The two main tools we used were accuracy and the confusion metrics. Accuracy is pretty straightforward. It's basically how many times the model was right, divided by the total number of prediction. The formula we use is this: accuracy, true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. And so after training all our machine learning models, we needed it give us this is what it give us. It give us a good general measures, but it's not always enough. So we also looked at confusion metrics, which show the number of the correct and incorrect predictions for each classes. Here you can see one confusion metrics from 9 for the random forest model, and also this one is from SPSS for the random trees algorithm. Moving to section 4 results, we started by examining the data set. We had 306 valid entries and a mix of numerical and categorical variables. The goal here was to understand the distribution and nature of each column before jumping into modeling. Here, as you can see, is the CPSS data audit table showing things like mean, max, mean, and skewness. In this table, we notice, for example, price transform had a high skewness of 3.625, meaning most prices were low, but a few were really high. And for size transform was even more skewed over 7, showing the most items were small in size. And reason for return had 15 unique classes, which tells us this is a multi-class classification problem. Here is a bar chart showing the class distribution. This gave us a solid foundation before we started building models. And section 3.2, machine learning modeling evaluation. In this section is where we really dug into performance. We tested a total of 7 models across both NIME and CPSS platform. This is the confusion matrix for NIME for random forex, and this in 9, yeah, and this is for NIME bias, and this is for decision tree. And also for SPSS, we tested C and R. Here is the confusion matrix, and here is the accuracy, and also we have for the random trees, for the child, for the 3AS, this is the last one, the 3AS. And here model comparison. So here what we did, what we did is we put the results into this comparison table. This is the comparison table for the both NIME and CPSS. So the best performance overall was random forest in NIME, which with an accurate of 76.87%. Decision tree had a higher score, but it likely overfitted. And here the interpretation. Okay, why did random forest do better? Well, it is an ensemble method, meaning it's built many decision trees and takes the average, which helps prevent overfitting. It works especially well on our mixed type dataset with both numbers and categories. And it handled important features like production place and product status with high accuracy. So overall, our project showed how machine learning can be used to predict return reason with a pretty high level of accuracy. We used multiple tools, compared results, and learned that model selection, feature pre-processing, and the platform used really affects performance. This is the workflows. And to wrap things up, we saw the random forest gave the best and most stable performance. And also features like production place and product status played key roles. And simpler models like naive bias didn't work well in our dataset. For future work, we want to add time-related features, maybe return trend over time. Also, try deep learning models and even build a live dashboard that classifies return as they happen. And this is our references. Thank you. This is the end of our machine learning presentation. Thank you for your attention.